As Lionel said, I'm an engineer, specialized in applied mathematics from INSA Rennes. And so I started to work for my company, which is called Charier, 3 years ago as an intern. And now I'm working full-time as a data scientist here. So my presentation will be about our project of predictive maintenance in public works. And the title I gave this presentation is Optimizing Maintenance and Avoiding Major Breakdowns of Construction Machines. I will do a little presentation of my company, which is called Charier. And then I will remind everyone the context of the project, because I already did a presentation last year, but I guess not everyone was there. So I will do a reminder about that. Then I will talk about the model we did with Lionel, and then I will do a focus on how we use it currently and how we plan to develop it in our company. So first, I will do a little presentation of our company. So Charier is a company of public works. So we have different fields of applications. So it goes from the quarries to the roadworks, dismantling, earthworks, civil engineering, and more recently, we are also doing some landscaping. So here's some key number from last year. So just so you can see the size of the company. So we are around 1,700 employees. We work on almost 60 different sites. So we have 15 quarries, more than 20 work agencies, and then we have some other sites for waste management or also asphalt plants. And so it's a company that was founded in 97, so more than 125 years ago. And it was founded by a member of the Charier families, and it's still a family-owned company. And also some of the members of the family are working in the company. It's run by someone who is not part of the family, but they are still owning the company. So they are now currently the 5th generation of the family who is owning the company. So here's a little map so you can see where our agencies are located. So it's mainly in the west of France, around Nantes for the majority, because this is where our head office is. And we also have an agency in Paris, and we also tend to do more work, more different works in Paris. For example, our agencies in Rennes and in Nantes do more and more work in Paris for specific works, for example, the civil engineering and great earthworks also. So now I'm going to talk about the Connected Equipment Project, which is the global project that includes the predictive maintenance project. So to give you a bit of context of why we are doing this project. So we have more and more machines that are equipped with telematic data. So I will talk about this in the slide after that, but this means we have more and more data about that, and also about plenty of other things. And so the goal of this project is to add value to this data. First, for example, for simple things such as fuel saving, or reducing our idle, that is to say, like when the machine is not working but the engine is still running. So we want to reduce that because it's very bad for the machines. These are, for example, simple actions. And then we can have that will be the goal of a predictive maintenance project, which is reducing the global cost of our breakdowns. So there is a small graphic about the cost of a breakdown, because there can be 3 parts that we can talk about for the cost of a breakdown, which is the first one is the direct cost, which is well known because this is the cost of the reparation of the machine. So if we have to change a part of the machine, or for example, if we have to change the motor, this will have a cost, and we also have to pay for the people that will be working to the operation. So even though we are lucky in Charier to have our own maintenance workshop, we also tend to work with the machine constructors, because for specific operation, we sometimes need to work with them. And there are the indirect costs. For example, it will be if there is a breakdown that will interrupt an operation for several hours, or sometimes one day or a few days. Well, then there can be a loss of production, or maybe we have to rent another machine to have a compensation for a breakdown. So this will cost us some more money. And then there will be the lifetime of machine that will be affected. If there is like too many breakdowns on the same part, it can affect the lifetime of this part of the machine, and then we'll have to replace it sooner than we should. So this will also cost us more money than if there is no breakdown. So you can see also on the bottom left of my slide, this is how we have the presentation of the telematics data in our CMMS, because we are in the same time developing a CMMS. So CMMS is a computerized maintenance management system. So the goal of this system is to have a system with all the information we need on all of our machines. Telematic data is part of this, but it's also, for example, the register of maintenance, global information of our machines, and also plenty of other information. So here's a quick view at our equipment fleet. I'm not going to go into the detail of every type of equipment, but it's just so that you can see which type of machines I'm talking about. So because we also have other type of equipment, for example, trucks, but they are not concerned by this project, because this project is really focusing on only construction works machines, for example, loaders, dumpers, excavators. So we have 60% of our fleet currently that has telematic data. So it's a number that will tend to grow over the years, because we replaced all the equipment that doesn't have telematic with new equipment that has it. Last year it was 55, now it's 60, and our goal is to have 100% of our fleet with telematic data. We tend to work with four major brands, which is our Caterpillar, Volvo, Liebherr, and Komatsu. And we also have some machines with other brands, but these are the four major ones. Now I'm going to talk more specifically about the predictive maintenance project and how it has evolved since I arrived at Charier, because I arrived 2 years ago as an intern to work specifically on that project. So to talk about a bit about the data that we will tend to use on this project. So I talked about the telematic data before, which can give us the number of working hours of the equipment, the fuel consumption, the geolocalization also. And there are also other data than that. So for example, the register of maintenance and breakdowns that we started. So the maintenance register was started more than 10 years ago, but the breakdown register started only 3 years ago with the development of our CMMS. We also have data from external partners, for example, with oil analysis. So in our machine, we have, for example, engine oil, or we also have oil in our hydraulic system. So it's very important for us to do a regular analysis of this oil and to see if everything is right with that. We also have the generic data on equipment, age, weight, type, power, and other things. We have reports from the field so that we can know which type of work the machine is doing. And then also the external data that we can get. So it will depend on what we need, but it's mainly the weather or the environment to know, to be sure of the environment that the machine is evolving in. So now I'm going to talk a bit about goals and difficulties of the project. So the original goal was to have a global model that could say which machines were more at risk to have a breakdowns, and the goal was to have a precise idea of the time of the breakdown and also the location. So when I say the location, it's like what part of the machine will have a breakdown. Is it going to be on the flexible, on the engine, the hydraulic system, or other things? So it's mainly the type of breakdown that we wanted to target. At the beginning, we had the classical machine learning approach, and it was very difficult with that approach because there are many different causes and different types of breakdowns. So that was the number one difficulty, the complexity and diversity of breakdowns. It was not possible to have a unique model that could represent the health of the global health of a machine. Because an engine and a flexible will have very different causes and very different evolutions So we cannot model different parts of the machine together in one model. And the second difficulty is the relatively low number of breakdowns registered, because I said we started in the beginning of 2019 to register our breakdowns. And so we have a lot of breakdowns registered, but as I said, there are a great diversity of breakdowns. So if we look at these breakdowns only type by type, and if we separate by different type of machines, then we realize that we have few examples of breakdowns by type of breakdown. So it's not possible to have enough data to have a classical machine learning approach about this. So I started working with BayesiaLab. So at the beginning, I was working with Emmanuel Keita and Michel Resch about still doing a machine learning approach, but with separated targets. So we separated the different types of breakdowns. So separated the breakdowns on engine and the breakdowns on the hydraulic system, flexible and electrical issues. So these four types were the four major types of breakdowns, but there are also other types of breakdown that we didn't take in account because they were less important. So we took the four most important, and we focused on these ones. And is that the lack of data on breakdowns was still a problem, even with the Bayesian network to do a machine learning approach. That's when we started to work with Lionel and use expert knowledge approach with BEKEE that I'm going to talk about just after. And before doing that, so we had to redefine the target and focus really on the most expensive types of breakdowns, because on the different types of breakdowns presented before, we realized that the ones that were really expensive for us were really the breakdowns on engine and on hydraulic systems. Because we realized that these are the most vital parts of our machines. If we already had a big problem on a hydraulic system, and sometimes we even have to replace the whole machine if the problem is too important. So then we see that this can have a really important cost for us. And so we tried to do a schedule. So the schedule was to do a first try on the modelization of hydraulic system of excavators. So that was the first model we did with Lionel, and I'm going to talk about it a bit after. And then after we did that model, we had the whole process of testing the model and starting to put it into production. And then we decided to extend that approach to do a model for the engines for all types of machines. And so we did that in June of 2022. And then our goal is to generalize that by doing models on kinematic chains, which will be related with the engines, but it will allow us to have specifications for all different types of machines. Because when we did the model of about the engines, it was really on a global model for all the types of machines, because the engine mostly have the same way of working. If it's on a dumper or an excavator or a tractor, it's still the same functionment. Whereas for the kinematic change, there are differences. And then we will want to generalize our work on hydraulic models or for other types of machines. So just to say a few words about the BEKEE approach, because Nel already talked a bit about it on Monday. So the first challenge was to have a good modelization of a complex system. So right now I'm talking about the model that we did on the hydraulic system of excavators. So you can see a scheme of hydraulic system. It's a very complex system. And our goal was to modelize all the symptoms and the causes that could lead to breakdown on that kind of system. So the methodology was to first do a brainstorming about all the different causes, then organize every different causes and symptoms in different blocks, and then build the link between the nodes, the block by blocks, and then build the block together. So I'm not going to go into the detail of the model because it will be very technical and it's not the main focus of the presentation, but you can see there are one big block about the pollution and contamination, because this is the most important part on a hydraulic system is to avoid the pollution on it. And then there are a block about the oil quality, because that's how hydraulic system works, with a flow of oil going all through it. So if the quality of the oil is bad and we have problems with that, then we can have a problem on our hydraulic system. And also then part about the maintenance. So how is the maintenance done on the systems, and the usage of the machine. So if the machine is used correctly and in the right environment. Because sometimes if you go to use it in a type of environment that has a lot of dust or something like that, you can have risk to have a contamination on the system, for example. So that's why we have this block. And also the weather has a great influence on that. So there it is. And then this is the second model that we did with Lionel, which is the model about the engine, sorry. So there, Lionel used the new methodology for the beginning. So the beginning of the session is always a brainstorming. So for the first one, everyone gave their opinion, and they were debating about it and trying to have the most possible nodes to start the modelization. And now for the second model, Lionel did this brainstorming with a BEKEE quiz. So that is to say, at the beginning, we were trying to see what were the most important parts about the engine and the most important causes about the engines. But this time, everyone was answering to BEKEE on the quiz, so that there was no bias, and everyone could express their opinion, even the one who were more introverted or shy. So they could give their opinion more easily. And we took note that this helped us a lot, and helped us reduce also the time of the first part of the session, which was to have all the notes and the different parts. So now I want to do a focus on how we used these models and on the IT integration of the model, because I think it's important to explain how we can use it in production. So I just put a few reminder about the goals that we had when we started this approach with expert-based modelization. So the goals were to have a model that was usable by the managers without giving them a lot of works. Because so when you do the training with experts, at the end we can use a simulator and fill the nodes by hand, if I can say it like this. And so you can do it for every machine, but it will take a lot of time for the maintenance workshop managers. So the goal for me was to use every data we have and that I talked about before, and use it to fill in the root nodes that we had in our model. For our hydraulic system model, and in the long term to have the result of this model in our CMMS. So because the goal of our CMMS is to have all the information of the machines. If a manager open the CMMS and open the section of one specific machine, then he will have all the information, and he will have something that will tell him the result of the model. Here for the hydraulic system, it will say if there is a risk about a breakdown on the hydraulic system. Just to talk to you about how we use it currently, is I do a weekly creation of evidence files to run the model on BayesiaLab. So I don't know if you guys already use this feature of BayesiaLab, but for now it's the easiest way for me, because we have a combination of internal data, which is, for example, telematics. We get it. We get it into our database. Maintenance intervention, we have it into our database too. So I can have this data with SQL queries. But we also have data that comes from other partners. For example, oil analysis, we do it with Total, which is a big French company. And so for now, we don't have this data in our database. I have to do a data post-treatment to cross every data and put it as the evidence file. So at the bottom of my slide, you can see how the evidence file is at the end of the data post-treatment. It's a simple text file. I'm sorry for you guys. It's in French because we have the name of the node in French and everything. But you can see the first node name. It's the name which is between the question mark. So it's the oil temperature. And then we have the state, which is normal. So this means on the first line. So each line corresponds to a machine. And on the first line, it means the machine has a normal oil temperature. And then we have, after, the other nodes information. So the goal of this evidence file is to have information for each node of the model and for each machine that is concerned by the model. And at the end, I put this evidence file as in BayesiaLab, so as shown in the right of my slide. You can see there is a section in data evidence scenario file associate. So I just associate this scenario file in BayesiaLab, and then I can run it, and this will give me a file with the output of the model for every machine that is considered by the model. That is to say, every excavators that has telematic data in our company. So it's around 70, 80 machines that is concerned by this data. When I have the result of the model, I communicate it with the manager that is responsible for the machine. So mostly right now, we don't have the result yet in our CMMS. So I call directly the manager and we see together what will be the problem, because the one advantage of the model is that we can easily see the cause of the risk. So, for example, if we have overheating on the oil, we can see it very well, and then the manager will take an action to prevent a degradation on the hydraulic system based on what the models are saying. And so I keep an update of an history of actions that are related to the model, because we use that to have a return, I don't know how to say it, like to see the model is working correctly, and if the data that is put into the model is good, and if it's really useful for the managers. So for now, this system is only about the hydraulic system, and soon, in a few weeks, I will start to do it for the engine model also, because I will soon have finished to put all the right data in the model. And I want to talk a bit about the data integration, and our goal is to have the most automatic system. So as I said before, we have some external partners. So we want to build an API connection with these partners so that they can give us the data we want directly into our database. So I'm working with the IT team and our IT team to reach this goal, and so this would allow us to avoid all the data post-treatment that I have to do right now. And so we could use an API to directly make the model work with the data from our database. And so doing that, we could directly display the result of the model into our CMMS without having to do the evidence file and run it on BayesiaLab. This will be an approach that will prevent us from doing weekly calls with the managers. Now they will have all the information on the CMMS. So for the hydraulic system and the engine and kinematic chain part. And then we also have the goal to display the main cause of the machine for the machines that are at risk, because for now I don't have a lot of machines that are at risk, because we are aiming at the big major breakdowns on machines. So fortunately, it does not happen all the time that we have a machine that is at risk. So it's really easy to look at the model and to see what is the cause of the risk. But then what would be the goal is to have that cause automatically displayed with the result of the model. So I think it should not be too difficult, because in BayesiaLab you can easily see for one model which nodes have the most influence on the result of the model. So we can use that, and then you can easily see which nodes have that is different from the normal user of the machine. And also, so I wanted to say a few words about how the modelization and the work we did with Lionel and the experts that helped us to build the model, how it helped us to target new type of data that we wanted to have in our CMMS. So for example, oil analysis, it's very important for us, but we don't have it in our CMMS. We have it on a website that is managed by Total. So for the maintenance managers, they have to go on another site to have the information. And it's the same, for example, for flexible intervention. We do it with Chronoflex, which is a company that has its specialization about flexible. So the goal is to put all this data in our CMMS and to have really all the important data in the same place. And also we tend to modify the way we register our maintenance intervention, because we realized we needed some few more information about the intervention. For example, if it's done in the maintenance workshop or if it's done on the field directly, and who is doing it, because we have our own workshop, but we also work with the contractors. So sometimes they do the maintenance and sometimes we do it. So we want to have that kind of information. And so here, so just to take a look at our CMMS, at the left, we have the telematic alerts that we can have on the machine. And so that was also a target that we had in the, after doing the modelization, we realized that these alerts were not really possible to exploit by the managers, because there was too much alerts, and sometimes we didn't even have the description. So now we have the description and it's clearer for them. And then on the right of my slide, you can see the oil analysis. So this is how it's presented on the total website. And so that's the kind of information we want to put directly into our CMMS. So again, I'm sorry, it's also in French because their website is in French. But what you can see, it's the rate of presence of metal in our oil. So for example, there is the first line is in red. It means that we have too much iron in our oil. And it means that the system is used too much, and it's starting to have a degradation of the system. And so it's really important information for us. And so we use it into our model for hydraulic system. And so the idea will be for the manager to have first the information from the model that will tell that the machine is at risk. Then it will tell him the cause. So that would be to say the presence of iron in the oil, and then he could directly see the complete analysis of oil to see if there are other problems, and then he can take the decision of how he's going to manage this problem. Is he going to change the oil or do another analysis or do an intervention directly on the hydraulic system? So that will be the final goal of our project. So thank you for your attention. I hope this was clear enough for everyone. And I see now if there are some questions about this presentation.